Good day, everyone. My name is Francisco Franco Jr., a faculty of the Department of Chemistry, De La Salle University. I'm here to present our DOST PCIEERD funded project, which was completed last year, 2021, entitled Electrochemical and Quantum Mechanical Investigation of Various Small Molecule Organic Compounds as Corrosion Inhibitors in Mild Steel. So here's an overview of the project in graphical abstract. So we tested several organic compounds as corrosion inhibitors in mild steel in a corrosive solution of hydrochloric acid, and we did several tests including potential dynamic polarization, linear polarization resistance, electrochemical impedance spectroscopy, and calculations under the density functional theory. This research employed a combined computational and experimental approach in finding potential small molecular organic compounds that potentially have high corrosion inhibition properties. Quantum mechanical calculations were carried out to determine the molecular properties of several small molecules which can be related to their corrosion inhibition properties. Chemical substances with favorable molecular properties were then tested for their corrosion inhibition efficiency via electrochemical measurements. Further understanding of the interaction between SMOCs with high corrosion inhibition efficiency and steel were carried out by analysis of the electrochemical measurements and further quantum mechanical calculations. Cyclic conjugated organic molecules have many interesting properties. For example, addition of heteroatoms may result in changes and enhancement in its properties. Due to their possible favorable interaction with metal surfaces, small molecular organic compounds may provide protection to steel surface and reduce its corrosion rate. Combination of theoretical and experimental methods may help in understanding and predicting the interaction of SMOCs and steel surface and effect on the corrosion inhibition properties. As we know, corrosion in steel is a global problem which can cost about $1,000 billion a year. Corrosion may lead to environmental problems due to leakage of hazardous materials. Protection of steel by addition of corrosion inhibitors, for example in coolants, fuels, hydraulic fluids, boiler water, etc., slow down the rate of corrosion by formation of protective layer on the surface of the metal and interfering with the electrochemical reactions occurring during the corrosion process. Current and widely used corrosion protection technologies such as chromates, phosphates are very effective but highly toxic. Thus, use of less hazardous organic compounds with similar corrosion inhibition efficiency is needed. I divided the project journey into 3 phases. First, the pre-implementation wherein the project was conceived. So I had experience on conjugated compounds, and I also did measurements previously on current and voltage. So I combined these two and I applied this on the corrosion problem. So the project was submitted to PCIEERD and was eventually approved. Next, project implementation. This is where we use a lot of time. So we gathered a lot of data, analyzed a lot of data, but this was also the time when the pandemic hit. So we had to stop for a while, but the project was extended, and luckily we were able to finish and gather the needed data. So we were able to write the manuscript, and we were able to submit the final report and other requirements for the project. So this was very challenging for me because this is my first DOST funded project, and there are a lot of administrative procedures that I haven't experienced, and of course the due to the pandemic. Here's a summary of the computational results. So we were able to calculate a lot of parameters from the molecules, and we also did experiments, and we were able to generate Tafel plots and Nyquist plots to determine their corrosion inhibition efficiencies. And we related the computational and the experimental results in order to determine their relationship. So we have several outputs. So we were able to publish in a journal and several conferences. We even have a TikTok video. So in conclusion, several compounds were tested for their corrosion inhibition properties and quantum chemical parameters and their relationships were determined. So in the future, we would like to test other molecular systems that may have good corrosion inhibition properties. We also would like to expand our data set and employ data science methods, for example, machine learning or deep learning. And we would like to collaborate with the industry or other institutions, or have research collaborations on computational chemistry, electrochemistry, and corrosion science. So that's it. Thank you, DOST PCIEERD.